Annie is an assistant professor for the computer science department at University of Toronto, and she has received her PhD from University of Waterloo in 2014 under the supervision of Professor Andrew K. Wong and Daniel from the Center of Pattern Intelligence and Machine Intelligence. Annie has also been a visiting researcher at Fields Institute and um, as well as a research scientist for Vertical Scope and Strategy AI. The audience would be able to post questions in the chat. You could take up when the presentation is going on or later. And handing over to you guys now.
Perfect. Thank you so much. And I just wanted to tell you that with me today are my colleagues as well as some trainees. And we're very happy to have them with us today. And I'll introduce you to them in the next slide. So welcome to our tutorial on neural machine translation for low resource languages. Neural machine translation has seen a tremendous spurt of growth in the last decade, and it has entered a mature phase. While neural machine translation is considered mostly widely used solution for translation, its performance on low resource language pairs still remains suboptimal compared to high resource counterparts. And this is due mostly to the unavailability of large parallel corpora. So there's not a lot of data available for low resource languages. So when implementing neural machine translation techniques in low resource language pairs, this has received some spotlight in recent research arena, leading to substantial amount of research reported on this topic. Our tutorial today presents a detailed survey of the research advancements in low resource languages for neural machine translation. And we might call low resource language LRL or neural machine translation NMT going forward, but we'll try to say the full thing whenever possible. And along with quantitative analysis, we also see quantitative analysis aimed at identifying the most popular solutions based on our finding from our previous work, which is a survey and a couple more papers in the work. This tutorial provides a guideline to select the best neural machine translate technique for a given low resource language data set. We also present a holistic overview of the research landscape and provide a list of recommendations for further enhancements of the research efforts. And lastly, we not only discuss the methods and the theories behind these techniques, but the practicality and the experience of the techniques based on our own experiences. So we are a group of researchers working on natural language processing. Sarangika is unable to be with us today, but with us we have Mariana and Shravan and Anthony and Ricky, and I'll let them introduce themselves each one by one. So Mariana, go ahead.
Hi, everyone. I'm very happy to be in this session and to talk about this wonderful project, which brought together all of us, despite distances, despite time and difficulties imposed by the pandemic. My name is Mariana Privtis-Kanduli. I'm an assistant professor at the University of New York in Tirana. And my research interests revolve around NLP. And yeah, I'm very happy to be here today and to talk about this research project.
Shravan?
Yeah, hello everyone. I am Shravan Nayak. I am joining from India, and I work as a software engineer at Microsoft. My research interests are mainly in machine translation for low resource languages as well as dubbing. Great to be here today.
Great. Anthony?
Hi, everyone. Nice to meet you. I'm Anthony. I'm currently a master's student at the University of Toronto and happy to be here today.
And lastly, Ricky.
Hi, everyone. I'm Ricky, and I'm currently an undergraduate student at the University of Toronto, and nice to be here today.
So this tutorial is mainly based on a survey review that our team conducted with additional few team members, Ravi, Shekhar, Marhin Alam, and Rishman G. Kerr, and Surangika, who is the main lead. So they're unavailable today due to the time differences. The later hands-on part of the tutorial has been based on a second our continual work on mBART fine-tuning with the state-of-the-art results from low resource languages. For the schedule today, you will see that we plan to have, right now we're going through the introduction of the tutorial, and then we'll introduce neural machine translation and the low resource languages. Then Mariana will introduce the landscape of low resource languages and neural machine translation and give you an overview of neural machine translation techniques and how to select the best technique for your particular low resource language pairs. Then Ricky and Shravan, they will go through the history or the methodology evolution of neural machine translation. They will introduce the sequence pre-trained models, how to adopt pre-trained models for neural machine translation with some tips and tricks. And then Mariana will close at the end with some open questions and future directions. And we'll open it up for Q&A at the end. So that's roughly the schedule today. I don't foresee us going more than an hour and a half to 2 hours. So I hope you really enjoy the tutorial and try the hands-on sessions with us. The learning objectives for the attendees of this tutorials are as follows. By the end of this tutorial, learners should be able to understand the neural machine translation techniques, what are the major techniques that can be applied to low resource language pairs, and what are the current trends ongoing. You should also be able to select techniques, so decide which one is the most suitable technique for your given low resource language. And then you should also know the future direction and determine how to increase the research efforts and what are the research directives for neural machine translation on low resource pairs. So since the beginning of time, language and communication has been central to human interactions. Therefore, translating between different languages has been critical as well as pivotal in societal and cultural advancements. Machine translation initially was the first application to be conceived solvable by computers, and it was created by Warren Weaver of IBM in 1954 as a word-for-word translation system. Following this, various techniques were developed to address the problem of machine translation. You can see next in 1993, statistical machine translation was created by IBM Brown Mercer. We had a really good session by Pascal Feng, who was one of the originators of statistical machine translation. Now, because the performance of these statistical systems is directly impacted by the amount of training data you have available, a heavy emphasis was then placed on creating translated data sets. So these are parallel sentences of translations from one language to another language and is known as by-text. Finally, in 2013, neural machine translation was introduced as end-to-end neural encoder-decoder. And these techniques saw a huge breakthrough with promising results, which was further popularized through various different new architectures. Currently, neural machine translation is the dominant technique in the community. However, these neural machine translation systems require a huge volume of parallel data to achieve comparable results to that of the statistical machine learning methods. So for many of the 7,000 languages that's currently used around the world today, the requirement of large amounts of parallel data set is not a realistic underlining assumption. So your high resource language pairs such as English, French, Chinese, German, they all have plenty of data sets because researchers have been creating a lot of data sets and parallel corpora over the years. But for your lower resource languages, this is considered a major challenge. And in recent years, there's been noticeable increase in neuromachine translation research in academia industry that specifically focuses on low resource language pairs. And we show that this trend in our exploration of low resource language publications in the community. So you can see this graph here. We first define low resource languages, and it's known as under-resource, low resource, resource poor, low data, less resource language, extreme low resource language. So you might hear all these terms flying around as related to low resource languages. And the criteria that researchers have tried to define these languages is maybe like the number of mother tongue speakers or the number of available data sets. Also, if the language lacks a unique writing system, so if it's spoken only, it's not written. If there is presence on the World Wide Web, so some of you might know that the internet is very biased or homogeneous in terms of types of people who are interacting on the internet. There's a lack of linguistic experts to a specific language or a lack of electronic resource such as corpus, vocabulary list. So those are all considerations for something to be low resource. So Joshi et al. In 2015 categorized 2,485 languages. So, a fraction of those, about, 1/3 of those languages into 6 groups based on the amount of publicly available data sets, specifically, on-label data, such as data that's in a single language, or label data, so like data that's in both languages, parallel data. So when it comes to translation, I'll just say as a side that, in NLP, usually you only need language and text in one language, but in translation, you need 2 languages. So that's the source language and then the target language. And very often one of these turns out to be English and the other one is the low resource language. So the amount of data then is determined by both of these languages, right? Both the source and the target. And the parallel translated text data corpora is called a bitext. And we use the phrase low resource language neuromachine translation to talk about these techniques that translate between low resource language pairs. And then another note about data is multilingual corpora is text of single language without the translation. And we don't really consider this in this definition, Joshi's definition here. So having very large monolingual, like single language corpora, but having low translated text is still considered a low resource language. So we only look at the translation, like two-way translation. So then a little bit more about then the categorization here, right? So we have, I'm giving you 3 here, medium, low, and extremely low. So high resource language is usually anything over 1 million pairs of translated sentences. But anything from 1 million to 500,000, that is considered medium. And then 500,000 down to like 1/10 of a million, which is like 100,000, that's considered low. And then anything less than 100,000, that's extremely low resource languages. So you can see this graph here by Joshi highlighting, a high resource and then extremely low resource and then everything in between class 0 to 5 here. And what they found is that there's a strong correlation between the language classes and the publicly available data sets. So you can see in the high resource language, we have, of course, English. And then over here on the low resource side, we have Sinhala, which is Soragika's language. We also have Taiwanese, which is my language, as well as some other languages here. A lot of the Indic languages fall under. Okay. And then, so in terms of spatial mapping, so this world map shows the spatial distribution, the geographical spatial distribution of the extremely low resource languages worldwide. So class 0 is extremely low and 1 is low. And then it's plotted with respect to the number of research papers that we saw. So we can see various regions. We have Asia, so quite a number of languages there. We have Africa. So this is by paper. So again, like very much bias on the attention of researchers. And then we have Europe. We have some things in Canada, like our native languages here in North America and South America. So yes, so Anthony is going to go next and tell you about 4 specific factors that is responsible for the growth of languages. Go ahead, Anthony.
Yep. Hi, everyone. So like Annie said, I'll be giving you an overview of the factors that are responsible for neural machine translation growth for low resource languages. Next slide, please. Thank you. So why is the landscape of low resource languages and neural machine translation important? Like Annie said, there's over 7,000 languages being spoken around the world. And a look into the related research reveals that neural machine translation techniques have mostly only been tested on the same set of a few dozen high-resource languages. We look at factors that affect the growth of research in neural machine translation research for low-resource languages. The box plot on the left shows Josh Yee's languages class versus the number of papers published in the area of neural machine translation. We look at the outliers, which are the black dots in the plot, and these languages seem to have more research on them than the other languages in their given class. So the goal is to understand what factors led to the growth of research for these languages when there are other languages in that class that are not as popular. And then hopefully we apply these techniques to other languages to improve the amount of research done on these low resource languages. So identifying reasons for this inequity in language selection would lead to efforts for more language diversity and inclusion in neural machine translation research. If neural machine translation has to be beneficial and advance society and the world, then it's necessary that all these languages be covered. To achieve this, we identified 4 important factors. So the first one is geographic considerations, the second being dataset availability, the third being open source frameworks and models, and lastly, community involvement. So first we look at the geographical considerations. To show the importance of geography, we looked at the outlier languages from all the classes with respect to their geographical location. Firstly, it can be observed in the bars on the left that for classes 0, class 1, and class 2, there's considerable increase in the percentage of languages that belong to Europe, nearly 25% in class 0 from that red bar that you can see there. This is mainly due to the availability of funds, resources, and regional level joint projects. The steady increase in the research activity for Irish and Slovene, which are outliers for class 2 and class 0 respectively, might be due to their presence, in the European region. Next slide, please. The next source of growth is driven by the availability of data sets. So for example, Sinhala and Nepali, which are outlier languages from class 0 and class 1, respectively, have seen a steep rise from 2018 onwards. One reason could be due to the release of the Floors Evaluation dataset, which includes both Sinhala English language pair and Nepali English parallel data. So our analysis revealed that the inclusion of a language in a standard yearly challenge, such as WMT, has a considerable impact on its growth in terms of neural machine translation. So like I said previously, Nepali and Sinhala were increasing a lot after 2018, and that's because they were included in WMT 2019 shared task. And then on the right, we plot the total number of data sets available versus a research activity. And this research activity is a number of Google Scholar results for neural machine translation for a particular language. So it can be observed that the availability of data sets is directly correlated with the research activity, which further strengthens our claim that the neural machine translation growth for a particular language is directly proportional to data availability. Similarly, the increase in the number of publications for the Gujarati language from 2019 onwards could be attributed to the fact that the Gujarati English language pair was included in the shared machine translation task in WMT 2019. So then the next factor is open source frameworks and model accessibility. So the availability of open source frameworks and models is a major contributing factor toward the growth of research in the area of neural machine translation. Frameworks such as OpenNMT, FairSeq, and Hugging Face provide an easy and scalable implementation that helps in building a baseline and improving it for existing and new languages. Since these projects provide standardized codes, it becomes easy to adapt them for low-resource languages, even by novice researchers. It eliminates the need to develop the codes from scratch and helps in accelerating the research process. Next slide, please. And then the last growth factor is community involvement. So a recent development is a group of like-minded researchers coming together to increase the visibility of machine translation systems in the context of languages used in a particular region. It consists of both dataset building and the development of standardized code. One of the prominent examples is the Mazikane project, which works on African languages. Within about 2 years, the Mazikane community has covered more than 38 African languages and resulted in multiple publications. So Swahili and Hausa have a steep growth factor after 2018, which coincides with the inception of this project. So overall, to increase growth in research efforts for low resource language, the neural machine translation community should come together on curating data sets and improving the performance of neural machine translation on these languages. These works should be open source so that others can also leverage them and continue the development cycle.
Great. Next, we have Mariana to tell you about neural machine translation techniques, the overview, and the landscape.
Yeah, thank you, Annie. Well, heading over to the next slide, I'm trying actually to give you an overview of the NMT techniques used for LRL translation. Well, NMT techniques or methodologies, if you want, fall broadly into supervised, semi-supervised, and unsupervised ones. To start with, I'm going to start with the unsupervised NMT techniques, which basically can be employed in the extreme case where no parallel data is available. In this case, monolingual corpora are easier to obtain than parallel corpora, even more so for LRL pairs. So hence the popularity of the unsupervised NMT techniques that use monolingual corpora or simply cross-lingual word embeddings. When it comes to architectures, most of them are those applicable to unsupervised NMT, make use of the adversarial frameworks of generative adversarial networks, or simply GANs, and contain basically the three popular steps like initialization, back translation, and discriminative classifiers. But without going into too many details, what I can say specifically about unsupervised NMT is the fact that in contrast to unsupervised techniques, we have these semi-supervised techniques, which assume the availability of some amount of parallel corpora alongside monolingual corpora. Semi-supervised techniques can be categorized according to the way the monolingual data is utilized, and they basically allow for the combination of parallel corpora with the monolingual data if the available parallel corpora is small. However, if parallel data is available, building NMT models between each pairs of languages is not really practical. Moving forward to multilingual NMT models, which represent another solution, we can say that this kind of technique facilitates the translation between more than one language pair using a single model. Most of multilingual NMT models are based on supervised NMT, while some research recently is available on the applicability of semi-supervised and unsupervised NMT in multilingual settings too. Although multilingual NMT models were initially introduced to avoid the need to build individual bilingual translation models, their capacity in the translation of LRL pairs is shown to be really promising. And recent research has also shown that multilingual models outperform their bilingual counterparts, particularly when the number of languages in the system is small and those languages are somehow related. Moving on to transfer learning, which is also another representative NMT methodology. This is commonly used in low-resource NLP, including NMT. Here, an NMT model is trained on a high-resource language pair, and then it is used to initialize a child model, this is how it is called, which reduces the amount of time taken to train the later, while guaranteeing better performance over the training of the child model from scratch. So the transfer process that takes form in NMT models can be broadly categorized as either warm start or cold start. And due to the availability of the child parallel data during parent model training, warm start systems are more accurate. And as opposed to that, due to the availability of child parallel data and parent model training, warm start systems are also more accurate. To conclude here, techniques, the zero-shot NMT represents a problem related to low-resource language NMT specifically. In zero-shot, we can say that the model itself is trained with no parallel data for the considered language pair, and multilingual NMT, unsupervised NMT, and transfer learning altogether have shown promising results for zero-shot pivoting and multi-NMT and unsupervised NMT and transfer learning. All this together are definitely identified as existing solutions in the literature for zero-shot NMT. Well, moving to the next slide, if we can, I'm going to show you an interesting picture where we have come up with a representation of NMT techniques that are applicable for the translation of low-resource language pairs. As you can notice here, the conventions that we have used, just for clarity, a single circle shape is representing a language, a double circle is representing a language with monolingual data resources. Dashed lines represent a translation task, while a solid line is representing availability of parallel data. Now, if you notice here, there are 5, let's say, individual representations. In the first one, in the upper left corner, we have, let's say, case A, where we have classical bilingual translation with parallel data available, followed by a semi-supervised technique where there exists a little bit of parallel data with monolingual data. In case C, we have the representation of unsupervised bilingual translation, and then followed by the multilingual, the basic case, where we can see that the translation between all 3 pairs exists there. And the presence of monolingual data. Note now that section or case E represents multilingual with pivoting from L1 to L2 through L3, representing therefore language 1, language 2, language 3. And we see there that there exists a high resource language presence. Well, this figure does not cover all the possible scenarios. There are many other variations and possibilities there. But yeah, for example, we can say that semi-supervised NMT techniques can work with monolingual data available either at the source or target size, and also multi-NMT works well with more than 3 languages. So please look at these representations and description of basic NMT techniques applicable for the translation of LRL pairs as let's say a basic representation. Moving on to the next slide. There's another very interesting graph that we came up with. This graph shows the number of Google searches for a particular NMT technique used for the low resource language translation task. Having covered all the possible techniques for NMT, we wanted to show that multilingual NMT had the highest number of papers till 2019. However, as you can see there, the unsupervised techniques have surpassed it marginally after that. In particular, watching at the graph, the use of multilingual NMT for LRL pairs started growing with the promising results shown by 2 papers from 2016 and 2017, the popular papers from Firat and Johnson. And something interesting happens in 2018 with transfer learning and semi-supervised techniques that had a similar growth, whereas in 2019 and onwards, transfer learning has seen a very steep increase in popularity. Well, to complete this observation of the data that we carried out of the research papers that were indexed in Google Scholar with this topic, data augmentation techniques seem to appear more frequently and to gain popularity in 2020 across Google Scholar papers or papers available in Google Scholar indexed there. And along with data augmentation techniques in 2020, looks like pivoting as well has lost its traction, which we believe may be due to the recent advancements of multilingual NMT, which basically outperformed pivoting for zero-shot translation. So overall, it can be seen that the interest of NMT research community towards the low-resource languages is steadily increasing irrespective of the type of technique. And in the next slide, we have also another interesting chart or flow chart where we actually tend to touch base again on the techniques and the effectiveness and the viability of those techniques that we covered so far in the previous slides. And we believe that this kind of effectiveness and viability of such techniques depend a lot on the size and on the nature of the available parallel and monolingual data, along with the computational resources at hand, which remains still a constraint for many researchers. In order to provide some guidelines to advise practitioners of low-resource language NMT on the suitable technique for a particular data setup, we came up with this representation, which shows basically a possible process that can be followed in this endeavor or in this quest of selecting an NMT technique. And basically, this flowchart provides guidelines for the bilingual scenario. And it should be also noted that if sufficient computer resources are available, the multilingual versions of all the techniques that can be used as they have shown promising results with respect to LRA pairs, are available here. And we did not show the multilingual scenario just for the sake of clarity here. We considered the availability and size of the parallel corpus, the availability of monolingual corpora, and the language similarity as the major factors to select a technique. And with these three main pillars in mind, we come up here with a, let's say, path where first we suggest the practitioners or whomever is going to refer to this guideline that if a parallel corpus is available for a language pair, the next step is to go and check its size. There is no definite threshold suggested in the literature so far for the size of the parallel corpus to be considered on a LRL scenario in NMT. However, here we considered a 0.5 parallel sentences as a suggested threshold, and this is not a hard threshold for a mere suggestion. If a particular language pair has more than 0.5 sentences, we can achieve a reasonable performance through supervised NMT techniques as indicated in step 2 here in this flowchart. So next, if the parallel corpus has less than 0.5 sentences, there could be multiple steps taken by a practitioner. One of the steps, for instance, could be to increase the size of the data set by using data augmentation, as indicated in step 3, which is also further followed by the supervised NMT techniques, as indicated in step 6. The other options could be to integrate the available monolingual and parallel data to perform semi-supervised NMT, as indicated in step 5 in this flowchart. Otherwise, if the source and target languages have parallel data available with some other common language such as English, then we can also recommend attempting pivoting as a way to sort out the problem, and this is clearly indicated in step 10. However, if such parallel data sets are not available, a practitioner can attempt transfer learning as indicated in step 11. So for this specific scenario, a parallel corpus between two high-resource languages can be used to build a parent model, which can then further be fine-tuned to LRL child. Well, if the considered LRL do not have parallel data, but they have a reasonable amount of monolingual corpora, in this case, unsupervised NMT can be applied, and this is shown in step 13. If a considered language pair neither has any parallel data nor the monolingual corpora, the only option is to manually create parallel or monolingual corpora. And this is exactly what we show in step 14. Well, out of this representation, this flowchart, we also want to show that there are two important remarks. First, the fact that for each of the discussed LRL NMT techniques, a large body of past related research is available. Therefore, practitioners have to carefully select the most appropriate technique to be used as the baseline for their considered languages. And the second important remark is related to the fact that LRL NMT should be considered as an iterative process. For example, if we go back to our chart, once a parallel corpus is manually created, the considered language pair now has a parallel data set of less than 0.5 M. So similarly to this, either transfer learning or semi-supervised NMT can be tried out. So yeah, there's a lot of room for interpretation and to drag down a lot of insightful indications and advice from this chart. We believe it was really a very important and useful representation. And with that, I pass it to Ricky for the next slide.
Thank you, Professor Scandoli. Now I'll be going over the history of neural-machine translation. So to start off, we need to define a neural-machine translation task. And a neural-machine translation system is implemented as a single end-to-end neural network system that directly translates the source sentence as input and target sentences as the output. Usually, translation tasks use sequence-to-sequence models, which has an encoder and a decoder, as you can see with the graph on the right. So the function of the encoder in red is to encode the source sentence into some fixed length context vector, and the decoder in green will then take that context vector and decode it into a variable length target sentence. So initially, such sequence-to-sequence architecture is implemented using two recurrent neural networks, one functioning as the encoder and another functioning as the decoder. Note here, in a recurrent neural network, at each time step, a RNN takes a word in and produces the next word. This is typically called an RNN encoder-decoder approach. Next slide, please. However, there are some drawbacks to this RNN design. So it suffers from the vanishing gradient problem, where it fails to capture long-term dependencies. Or in other words, the model is not able to retain information far back into the sentence. Hence, new design of hidden states are drafted in an attempt to solve this problem. Long short-term memory, or LSTM, and gated recurrent units, or GRU, are examples. These units train additional neural networks to decide which parts of the input should be remembered or forgotten. However, due to how RNN process information sequentially based on only the last hidden state, LSTM and GRU RNN sequence-to-sequence models still struggles with longer sequences of text, where the fixed-length internal representation failed to decode all words in the output sequence. Next page, please. So aside from LSTM and GRU, attention mechanism is another design that was initially introduced to improve sequence-to-sequence models. On the right, you can see the different encoder-decoder architecture between RNN and attention mechanism. So at the top, we have the RNN architecture, and recall that we only pass in the last context vector into the decoder. In contrast, at the bottom, the attentional mechanism gives an weighted sum over all the hidden states, which can be seen in the additional add and norm layer on top of the usual sequence-to-sequence architecture. So, in light of the idea of attention mechanism, the transformer model is proposed. Note that the transformer is a simple network solely based on the attention mechanism, dispensing recurrence entirely. Thus, it can achieve parallelism when we are translating. In addition, positional embeddings have to be added to the input and the output when training to avoid the loss of positional information. Observe on the right in the model diagram that there are also multiple attention blocks throughout the whole transformer model. So transformers have achieved promising results by surpassing LSTM and RNN-based models, successfully handling the longer sentences more effectively. As such, it has become the state-of-the-art paradigm for neural machine translation. Nevertheless, such large models would still require large amounts of data to train. So Shravan will now discuss how we can alleviate this need of data with pre-training and how we can perform pre-training and fine-tuning.
Thank you, Ricky. Now that we have learned a lot about low resource languages, the history, and some common architectures used, I'll be discussing about pre-trained models, which are like a hot topic in machine translation nowadays, how to leverage these for machine translation, and look into some code using which we can achieve this. Next slide, please. So yeah, instead of training models from scratch using parallel data, nowadays studies leverage the easily found large unlabeled monolingual data. Using this data, the main goal is to learn a good language representation that capture linguistic characteristics, lexical meaning, and semantic and syntactic features. So using monolingual data, today most state-of-the-art models have been pre-trained as a self-supervised learning task. So self-supervised here means that the training labels are generated automatically instead of manually annotating them. I'll be discussing more of this in the subsequent slides. But before that, let us look into a few different types of pre-trained models that are used. Next slide. So yeah, the first category of models are an encoder-based pre-trained models, which consist of an embedding layer followed by a stack of encoder layers. So the output that is obtained from the last encoder layer is used as the final contextual representation of the input. Examples of these encoder-based pre-trained models are BERT, Roberta, Electra, etc. The second category is the decoder-based pre-trained models, which consist of an embedding model followed by a stack of decoder layers. This is very similar to the encoder-based models. The main difference is the way the two models are trained, where encoder models can have access to the entire sentence, whereas the decoder models can see only the past and not the future. Examples for decoder-based models are the GPT series of models. And the third, something which we are going to talk more today, are the encoder and decoder-based models, where you have an encoder that encodes a sentence and then an autoregressive decoder that generates translations or representations for a task. Yeah, next slide, please. Now we will take an example of encoder and decoder models to understand how pre-trained models are trained. So to train a pre-trained model, the first step is to corrupt the input text with an arbitrary noise function. To the right, you will see a table where there are a lot of noising functions mentioned, like token masking, where random words are masked before sending it to the encoder, or sentence permutation, where the sentence phrase ordering is changed. So this corrupted text is then fed to the encoder. Once the encoder has encoded the text, the second part of the training is to learn a model to reconstruct the original corrupted text, which is done by the decoder. So once this whole task is completed, we will get a model that is able to take partially noised input and predict the denoised words to recover the original sentence. Subsequently, in all the applications, this is called as a pre-trained model, and we will be leveraging this for different tasks. Next slide, please. So here you can see some of the popular pre-trained models that are available today. You can see the BART series of models by Facebook. mBART is a multilingual version of it. So whenever a pre-trained model is trained for more than one language, then it is prefixed by a small m, which stands for multilingual. Then we have the T5 series by Google, similarly MT5, MT6, BYT5, etc. So all these are pre-trained models. The difference in them is that they are trained for varied number of languages. The noising functions are used are different, and the number of parameters used to train the models are different. So can we go to the next slide? So now, once we have used the denoising strategy to pre-train the model, The question comes is how to leverage it for the different tasks. To do so, we use fine-tuning to adapt the model to a desired task. We will look into this in more detail in the context of NMT. So in this figure, you can see that, using the denoising task, using monolingual data and the denoising task, we already pre-trained the model. And the next step would be to retrain the model for a desired task, which we'll discuss about NMT here. Next slide. So yeah, firstly, in the case of encoder-decoder models, we take the pre-trained model, which let us say, for example, mBART, which we'll be using throughout the tutorial, and initialize our new model encoder and decoder with the pre-trained weights. So once we have initialized the model with the pre-trained weights, we'll further train the model for the translation task using parallel data. So this is how the general flow of fine-tuning goes using pre-trained models. I believe now I will be sharing my screen, and I will go through a few code examples that will make this more clear. Please let me know when you can see my screen. I hope my screen is visible, right? Hello. Yes, thank you. So there are several frameworks using which we can train an NMT system, or leverage pre-trained models to train an NMT system. I'm going to talk about two such popular frameworks, which is FairSeek and Hugging Face, which we have used regularly in research. So in the interest of time and the resources available, I'm not going to run the code, but we'll make these notebooks publicly available so that you can experiment with it. So the first step of training the model is to set up your environment, and here we use FairSeek. So we clone the repository and we install it. Once we have installed it, we need to choose the model of our choice. Here we are using mBART 15 model. So FairSeek provides pre-trained models, and we can download it and we extract it later. So now that we have the model in hand, so in order to train, for example, say here, in this whole notebook we train for Sinhala English language pair. So to do so, we have to follow four steps in FairSeek. The first part is to encode the data. So what is encoding? So encoding is nothing but tokenizing the raw text using a sentence piece model. So sentence piece model is a widely used and a popular subworld tokenization and de-tokenization algorithm. It is currently used by most language models and other techniques to tokenize sentences. So every trained model will come with its own tokenizer that was trained for pre-training the model, and we'll be using that here. But if you want to create your own tokenizer, FairSeek also provides you the option to do that. So along with, so I'll be discussing command line scripts here. So FairSeek provides this code called spm-encode.py, which is in the FairSeek repository, that will do this whole task of encoding, that is tokenizing the data you have. So to this script, we give as input model, which is your mBART 50 model, the model which is your sentence piece model that you obtain when you download the mBART 50 pre-trained model. Then the inputs, which is the parallel text that you want to encode, as well as the output, that is where do you want to save this encoded outputs. You do this for all train, valid, and test set. So what this basically does is it tokenizes the data and stores it in a textual manner in text files, and you will be able to access it also. So once we have encoded the data, the second process is pre-processing the data. So why do we need to pre-process? As I said, encoding the data tokenizes it and saves it in a textual format. The computers can't read textual data, so we need to convert it into tensors, and that is exactly what is done by FairSeek pre-process. So this command line code will take the source language, target language, as well as the path to the train, valid, and test encoded data and create pre-processed data for this. So one thing to note here is that for most of the pre-trained models, there is already a dictionary. A dictionary is the mapping between words and numbers that the words are converted into. So if say you don't have a pre-trained model, you can ignore these two parameters, and the dictionary is created automatically for you by FadeSeek preprocess. So once we have pre-processed data, we have tensors, and the next step we use is to train the models. So training is also fairly simple. So we have this FadeSeek train command, which takes the path to your pre-processed data, and then a list of other parameters for which you can find very amazing documentation in the FadeSeek official repository, and then it trains the model. So some of the important parameters are, the path to the pre-trained model. This is the path you give to whichever model you want. Here in this example, we have taken it as the mBART 50 pre-trained model. But if you want to use any other model, that is the path you give here. Secondly is the saver, where you can where the checkpoints have to be saved. Then you can even set all the hyperparameters. One essential suggestion here is that you choose these hyperparameters from some research that has already been conducted, because training mBART and MT5 are not are a very resource intensive task. So it is better to take something that is standardized. So yeah, once this script runs and you have a trained model, then the next step would be to generate translations. So that can be done using FadeSeek generator. So what FadeSeek generator takes is, it takes the path to your data, which is basically the path to your pre-processed folder, and then it will take the path to the model and a source language, target language, and then generate the outputs or the translations for the test set. Here, to control which set of data you want to translate, you use this gen subset argument. Here we have given test, so it will look into this pre-processed folder and get the test data, and it will generate the output. So once you have generated the output, you will have something like this, generated predictions with all the translations. Okay, so then the next question comes is how to evaluate. So there are multiple libraries present that evaluate, and I'll talk about evaluation more later slides. We use Sacred-Blue to evaluate our machine translation outputs, that is to get blue scores, SP blue scores, etc. We'll discuss that further. But one common thing that is there is, what if you have some raw text and don't have pre-processed data? So in that case, what you can do is take the raw text, encode it using SPM encode, and instead of using FadeSeek generate, use FadeSeek interactive. So what FadeSeek interactive actually does is, it takes sentence as an input, but you can bypass that using this command or using the -- input flag, where you can pass the raw text file to the command. Besides this, it takes the model, the preprocessed folder, just like FadeSeek generate. So as you observed here, FadeSeek is quite simple. So it takes only 4 steps to fine-tune the pre-trained model for the NMT task. And this is something we have extensively used in our experiments. Other popular framework that exists today is the Hugging Face framework. And Hugging Face also provides some excellent code to use the pre-trained models and further tune it. So we used, there are several ways to do this, but the one which we popularly used is something that I'm highlighting here. So firstly is to prepare the FadeSeek data. So Hugging Face data takes text files. So it takes one text file for the source sentences, another text file for the target sentences. This is for FadeSeek. But for Hugging Face, we need to give a JSON file, something like this. So it will be, every line will be a JSON object which will have translation as the key, and the value will again be a dictionary which will have the source language and the sentence, and the target language as a sentence. So this is quite straightforward to create. So once you have the data, similar to FairSeek, we first set up the Hugging Face library by cloning the repository and installing it. The installation instructions can be found on their GitHub page. And once we have installed, uh, in, in the Hugging Face repository itself, they have an examples folder which contains scripts to run fine-tune translation models. So in most of our experiments, we have leveraged this script because it provides sufficient parameter tuning capabilities that we can customize our fine-tuning process. But it is still a very high-level script, so that it is very easy to train, and it provides it is a standardized tested script by Hugging Face. So to run this, again, it is very simple. So you just have to run Python run translation.py, give the model name. So here we have used a publicly publicly available name, which is Facebook mBART 50 large. But say you have your own pre-trained model somewhere, you can give the path to that model. Then there are a plethora of parameters, and you can refer to the documentation, like very good documentation given in the run translation.py file itself to set your parameters, source language, target language, whether you want the output should be predicted. So this script is an end-to-end script where you just give the model you want to train as well as your train, test, and dev path, and it will train the model, evaluate the model, generate the translations, as well as score the translations for you completely. So this is something we have extensively used in very large-scale experiments because of its simplicity. So it is not only limited to mBART 50, so you can train MT5 models like here, as well as BYT5. So BYT5 is a tokenizer-free model, another pre-trained model. So you can fine-tune even these models. So one more thing about Hugging Face is, say once you have trained the model, and you are not like a command line guy and person, and you are like a Python person, they give you tons of APIs to load these models and load the tokenizers, and then generate translations using using Python. So to do this is very simple. So you have to import some APIs like mBART for conditional generation, which is a model class, as well as the tokenizer class, which is mBART 50 tokenizer class. Once you have loaded your model, so again here we have used the publicly available path, but you can use the path to your tuned model here, and you load the tokenizer. Then you can simply tokenize your sentences, use model.generate to generate the tokens, and again bash decode, which is the it performs the detokenization process to get the final outputs. So yeah, again, Hugging Face is also very simple. So this tutorial only assumes a single stage of training, but if you want to do multiple stages of training, what you have to do is just replace after every stage with a new model name and tune the parameters as per your convenience. So so yeah, yeah, the notebooks will be publicly available. So we'll create a repository for this and add all the code there. So the next task is the difference between. So I'll be discussing some tips and tricks that we have used, the problems we have faced while doing large-scale experiments, as well as solutions to those. So one of the tricks that we used, because we had limited GPU capacity, was this mixed precision fine-tuning. So what happens in mixed precision fine-tuning is, instead of using 32-bit floating point, it uses a combination of 32-bit and 16-bit floating point arithmetic to train the models. So we haven't observed any drastic decrease in scores using this technique, but we did observe a shortening of our training time and lower GPU requirements, because mBARTs are like, mBART model is like very huge, and it is not possible to train it in Colab also. So you need a lot of GPU memory, at least 24 gigabytes. So using these techniques, they are very helpful. Secondly is the score calculation. So as I mentioned earlier, we use Sacred Blue library to calculate all our scores. So there are different types of scores that you can perform. Some of them are Blue, SP Blue, and CHRF. Um, how do we calculate this scores? So you take you install the Sacred Blue library, and then you give it the path to your ground truth as well as the path to your translations. After the minus n parameters, these refer to the the type of scores you want to generate. So CHRF is a tokenizer independent score which generates scores on a character level. Blue it tokenizes the text first and then calculates scores. So this tokenizer parameter determines what will be the tokenizer method to use. Here it is SPM, which means that sentence piece model. So we'll be calculating SP Blue using this. And finally, you give a path to save your scores, and you get all these scores easily. So some of the we have trained very large scale experiments with more than 1,000 experiments at times. So and these are some of the things that I think challenges we faced, and something that we must also consider while training such experiments. So one of the first recommendations is to first run small experiments that are representative of your whole training. Do some sanity checks on these experiments, and then run the experiment on a large scale. This is because if you directly run a large number of models, a small mistake in code means that you'll have to rerun these experiments again. And like we have suffered through this, we identified bugs after running hundreds of experiments and then only to rerun the experiments again. So this can be avoided by this technique. So what are some of the sanity checks? And this is through some personal experiences we had. So firstly, most of the times we generate bash scripts and submit it to a cluster. While doing so, we need to ensure that we are using the correct model path as well as the training and testing path. So a very funny incident that happened is when we were training one of the models. So we obtained really good scores for one of the languages, which had in literature very poor performance, and we were like very happy that did our technique just achieve state of the art scores. But we only found out that the paths were slightly incorrect, since it was written programmatically, and that is why it was achieving very high score. This was like one of those extreme fun moment and then go down side of situation we had. So it is very good to double check the paths you have given in all these experiments, because they can easily go wrong when you are running large scale experiments. Second, very important is to check your logs and to see if the model is overfitting. So if you are especially running experiments with varied dataset sizes, so this can happen that you always set a number of parameters to train your model, and even though you are using early stopping, your model may overfit a lot. So always keep monitoring the evaluation logs through the logs, and ensure that the model does not overfit. This is because even though you will not observe this in initial stages of your experiments, but when you are writing a paper and plotting graphs, you will see some outlier points. And sometimes they may be actually outliers, but many a times in our case we have found that the model was just overfitting. So it is always good to check this. And the third thing is that third sanity check is to go through the logs once. Even though if you are running the experiments alone, it might be very difficult, but if you have multiple collaborators doing it together, always sit together and go through the logs of the experiments to check that everything is proper. So once you do this, then you can run your experiments on large scale, just schedule it. And this seems to be a very good way, and it is working for us as of now. So and one last point that I want to highlight is always have a good way to organize your result, because training NMT today, like I remember back in 2017-18 when I first started, we used to have these LSTM models, and they used to finish training by an hour or so. But in the current context of these huge models, they take days, if not weeks, to train these models. So it is always better to have proper Excel sheet, proper GitHub repositories where you log the results very well. Otherwise, you run something today, and 1 month later you will not even be able to remember, for what you have run the models for. So I'll show one of the patterns that we use in our case. So if you look at, so we have this repository for tracking experiments where we have the languages which we have run, followed by the data sets which we have run, the sizes for which they have run, as well as the data sets which they have been tested on. And in that we have everything, so from prediction results to generated predictions, scores, as well as true translations with which we compared on. So the good thing about this is it ensures that if somebody questions the results, we can always give them the translations here, as well as our collaborators can come and check if there are some irregularities. Another major advantage of documenting in such a way is that now that so okay, when you're finally publishing or writing a paper, you'll have to draw graphs and charts. So this folder structure is a very standardized way which you can easily parse to get the results instead of manually typing everything. So yeah, so I'm reiterating the importance of documenting results, especially when you are running large scale experiments. Yeah, that was all from my side. Now handing over to Professor Mariana again.
Okay.
Discuss
Thank
directions.
Thank you, Shravan. Now it's time to wrap it up and to discuss the open questions and the future directions in LRL NMT research. We'll also take the chance to go back to our initial research questions and emphasize answers that we came up with. But before we go there, I just wanted to stress that while notable advances have been made in LRL and NMT in recent years, which is something that we also figured out in this endeavor, in this survey, there still remain interesting directions for exploration and model improvement, as well as in terms of equitability and inclusivity. So improvements to neural machine translation engines in general will fall into two main buckets. And the agreement among research scientists is that the first bucket has to do with accuracy. These problems, the NMT problems, are largely met with engineering solutions that offer incremental improvements. This applies to high resource language pairs like English, Spanish, German if you want, but especially to low resource language pairs. Well, the second bucket is around understanding, meaning, and the main challenge is helping users find their voice in another language, which is pretty practical in real life. And the one-size-fits-all nature of the NMTs today erases exactly this individual's personality and hinders their ability to engage in another language. That's why the long-term goal is basically to move NMTs towards something closer to the way human interpreters work. That's why the whole, let's say, future direction and future challenges in NMT-related research are actually channeling the path and are setting new standards and new challenges along the way. However, going back to our research, we identified multiple research areas for the research community to collectively increase efforts, especially on low resource language NMT. And these initiatives were broadly categorized as model improvements and equitable and inclusive access. Moving to the next slide, I'll highlight quickly challenges and opportunities we realized along the way. We believe that extensive evaluations to determine the impact of different impact factors that affect NMT performance, especially LRL pairs, is needed in order to point the challenges and opportunities along the way. better interpretability of the NMT models will help a lot supporting the whole process of low resource language translation, which is powering and in a way supporting the whole process. And creation of high quality data sets that include low resource languages has to take the amount of the right amount, the right share of interest and focus, because the highest the quality of data sets, the more promising are the results. And along the way, equitability and inclusivity are also some important factors. We believe as well that research on new model architectures that are being presented every day would definitely benefit the future and help at least tackle better challenges posed by this task. As we move forward to the next slide, exactly, to model improvements. I'll move to the next one because this is a wrap up. Yeah, exactly. I'll step into model improvements and equitability and inclusive access just for the sake of the importance that we believe it holds exactly with regards to future work. Especially we figured out that model improvements represent an important endeavor to be followed in this task. Based on the various LRL NMT techniques that we discussed so far, there exist multiple improvements that can be applied to the model, starting from allowing the multilingual models to include more LRL pairs, going to making the models more robust to limitations in the input data set, up to expanding the interpretability and explainability of the model in understanding their behavior and mitigating the biases in the model. Well, indeed, we believe that model improvements can be achieved by soliciting or infusing our impact in 4 different directions, starting with modal capacity to include low resource languages. We believe that massive multi-NMT models represent a promising technique, especially for systems produced by multinational tech companies. In particular, multi-NMT for zero-shot translation, for instance, is an important line of research as it eliminates the need for parallel data sets between every possible language. However, despite multilingual NMT being able to cover about 100 languages, only a small fraction of LRLs are included from the more than 7,000 possible languages worldwide. So more efforts need to be invested in this regard in scaling multi-NMT models that are capable of handling a larger number of languages, which would inherently cover also the LRL languages and extremely rare languages or resource languages as well. As to the model robustness to limiting input factors, we believe that techniques that we discussed so far are limited by various input requirements, being the size of the data sets, the domain of the data sets, and the language relatedness. So with these 3 in mind, it's important to recognize the challenge and to address it accordingly, because, for instance, there might not be sufficient or exhaustive resources in terms of domain relatedness. Most publicly available data sets are from sources that do not resemble real-life translations. Thus, more focus should be given to multilingual domain adaptation research, for instance, where pre-trained multi-NMT models can be fine-tuned to the task at hand. And moving down to the third, let's say, direction we can solicit in order to achieve model improvements, let me talk about the interpretability and explainability. Explaining and interpreting neural models is definitely a challenge for researchers in deep learning at wide, and more specifically in low resource languages, NMT. And for multilingual NMT, there have been experiments that go deeper into models that examine how language can be parsed, and the learning process, how does it really take place, and how different languages behave, and how do they relate, and whether they relate or not. So there has been a lot of attempts to provide theoretical interpretations on aspects of NMT models. However, we believe that more research in NMT model interpretability has to be basically provided. Mitigating model bias, though, is also a direction to follow, because we have enough evidence so far that gender bias exists, geographical bias exists in NMT models when trained on high resource languages, right? At least there is more evident. But recently, the existence of biases in the context of low resource language NMT is a problem that has not come into light as far as we know, but the lack of research or the lack of evidence doesn't mean that it is not a problem, or it is not going to hurt our model performance or accuracy. So in particular, when translating between languages belonging to different regions and cultures in multilingual settings, which appear to be far more promising for the time being, there can be a lot of undesirable influences from high resource languages. And parallel data extracted from web sources tend as well to contain a lot of bias. So, a lot of efforts should go to constructing data sets that are reliable in that sense. Let's move further to the next slide, where I want to highlight the next direction where we believe that future, let's say, work should be centered. With regards to equitable and inclusive access, findings in our trend analysis that we shared before suggested that more resources should be made available to underrepresented geographical regions, especially for traditionally excluded communities in technological development and those facing social economic inequalities. So the inclusion of these communities can be prioritized, and especially when creating data sets and providing accessibility in terms not only of resources, but especially in terms of computing resources that are required to building time-consuming and expensive neural models. These communities will benefit also from open source tools and frameworks and availability of trained models. More specifically, with open source tools and frameworks, we refer to tools and frameworks that are critical in advancing the field of LRL, or that can help building and creating data sets for those low resource languages. So basically creating and making them open source and for free available to a great majority of communities will definitely benefit the related community as well as the related research. So availability of trained models as well, we believe it's an important aspect in terms of equitable and inclusive access. The community has recently focused on developing computationally efficient NMT models. The public release of large-scale multilingual models has been limited, but recently, we have some examples from big tech companies. But it's needed actually to give more focus to that. and to provide more public access to these models, because these time-consuming and expensive models can be used as the parent models to be transferred to the LRL child models that we have in focus. Well, this can help a lot, especially to those working in LRL NMT, and as well as advancing the field in many other related areas. To conclude, it sounds sad, but it's still a reality. We still suffer the availability of computational resources. The community, especially that community that is covering the LRL NMT research, has recently focused on developing computationally efficient NMT models and providing computational resources for researchers. So the research community and the industry organizations and governments must put more effort into distributing these resources evenly. And next, to the next slide, we want to reiterate quickly and refer back to our early introduced research questions. The key findings of the survey paper project that we held can be summarized into three main directions. As to the techniques and trends, our survey revealed that there's a lot of LRL and NMT research, so this is definitely a field of research interest that is grabbing a lot of attention. And the trend, is still present and growing. With the exception of pivoting, all LRL NMT strategies, from data augmentation to unsupervised, semi-supervised, multi-NMT, and transfer learning, exhibit a onward trend in relation to research publications, indicating that these techniques have become the de facto solutions with regards to LRL NMT task. Well, if we go to the technique selection, which again remains a solid question, a solid research question, the decision chart that we propose can be used as a reference in choosing the best NMT approach for a specific data setting, while also taking into account the availability of computational resources. We do, however, draw attention to the fact that this choice is also influenced by other factors, such as the domain of the data and the relatedness of the languages and scope. Well, regarding various LRL and NMT approaches, several other factors were discussed in the survey. And for all of you that want to discover more about it, please refer to the paper. Moving to the last slide, a few comments about the future directions that we came up with. We identified a number of areas for the scientific community to focus further on the LRL NMT research. And these findings were broadly categorized as access enhancements and improvements to the models. More specifically, we believe that, as listed here, in investigations or endeavors to be followed, such as the efficient NMT inference, or making use of multilingual and monolingual data, exploitation of multimodality in NMT, which I believe is definitely very, very promising. NMT with background modeling could be a path to follow, and domain adaptation models will bring about a lot of insights and benefits in this task, along with explainability and robustness of NMT techniques and methods. To conclude with, let's say, a high hope on future NMT architectures, which can bring a major effect and impact, positive impact in revolutionizing the low resource language NMT research. And with that, we conclude here the presentation, and I pass it to Annie for the question and answer session.
Thank you, Shravan, and thank you, Mariana, for staying up late over your time zone to make this to give this presentation. Are there any questions? I'm looking in the chat, and we just have one from Sana that we answered. Okay, if there are no questions, then I will let you go enjoy your lunch. And we thank you very much for your time. I hope that was helpful to you to bring attention to this low resource language problem. Have a good afternoon and rest of the summit.